Oh, good morning. I haven't done anything on here in a little while. I figured I'd come back on and toss a few things out there from the brain, from the mind of Pops. Get my sip of coffee in. Tom's Cards and Gifts and Coffee. Snickerdoodle. Yeah. Anyway, I started thinking about a lot of stuff because I bought a gauge set, cheap one to put in a skid steer that their electronic panel has died. New Holland, and then safety and everything's intertwined. I think I have a way to take care of the safety part properly, but we'll see how that works out. Next, I wanted to be able to, there's no specs on the gauges. There's only two that are worth a hoot. The voltmeter, you just hook it up and it works, but there's temperature, and then there's pressure, oil pressure. So this is a very common one. It's probably a standard, but there's no markings anywhere. So what good is it? Well, I want to be able to check it, write down the resistance at 0, the resistance at, say, 20 psi, the resistance at 50, just to give a baseline. And you say, well, how do you know? Well, the gauge goes to, let's see which one here, 100 psi. You say, well, maybe that's not enough. Yeah, and the skid steer, yeah. The Shibara engines, they barely run 50 half the time. But they'll go high in cold weather. Temperature, that goes to, well, now, aging thing, to 50. So I've got plenty of room there. It always bothers me with voltmeters that they show the minimum is 10. You know, manufacturers, are you idiots? The minimum is 12.5 to function. So you got to at least start it at 12 and then take it up to 14.5. But they read it out at 14. You know, call me nuts here, but sometimes these engineers, but it sells. So what are you going to do? And they've got the red range for water at 210. Yeah, that's okay. It's a little high, but that'll do. You say high? Yeah. A lot of farm equipment, if you don't keep it under 200, you're going to cook it because you need that extra 5 that you're going to overheat something in the weather. But still, 210 will work. The funny thing is, some of the newer engines, like the Cummins, they won't even redline the bugger until, well, they will quite earlier, some of them than I thought they should. But they'll say 210 is an overheat, and the warning pops on at 215. You know, it's like, okay. I don't know. That's like passing a tree. Whoosh. Lost air for a second. Ding! Well, got these two English shepherds that are in the middle of their shedding season. What did I come on today for after all that? Well, the pressure gauge got me thinking. The formulas. Parker has one. I did a search, 0.7854 formula. Then it comes up 0.7854 times the diameter squared. Now that's the part I always missed in the formula in probably the last 30 years or so. Before that, I had a pretty good memory about it. And what is it? It's the area of a circle. The idea is to find area, and it's another formula. Instead of pi r squared, it's easier to measure diameter than radius. So what are you doing? Well, your pumps are oblong shaped, right? So you're guesstimating the length, the width, and kind of mellow it out. Well, what can you do? Pi times the diameter squared. Just measure an approximate circumference and divide by 3.14. And you're going to get a rough diameter. Well, now you can diameter squared times 0.7854 gives you the area. Well, what's the pump output? Well, if you want to know in cubic inches anyway, what's the depth of the pump? Because you got the area. Now you've got the depth of your gears or veins or whatever. Piston pumps, that's a whole nother deal. They usually go by a theoretical value, but you can do it your way of just put it in there, make a mark, 1 revolution, and see how much oil comes out. 0 pressure, full stroke, and that's, they're going to give you that as your initial assessment for your pump output. Why am I going through all this? Well, because both in hydraulics and electrical, there's some numbers that we're going to be playing with that are important. No, volts are relatively, the electrical side is very simple. And the hydraulic is too as well when you get down to it. But anyway, what you're looking at, say the electrical side first. You want volts, amps, ohms, and watts. Okay, volts, that's your voltage potential difference between the positive, where we theorize or we assume that power goes out. It's actually reversed. But let's play the game. Positive is positive ions, so it goes out, comes back, and when the energy is used, it's 0 volts here, or almost 0, and it's the difference between the two is your voltage potential difference. Scientists love the more words. Watch iRobot, you'll understand in the first half hour or less. She goes through a 30-second long description of what her position is and says, oh, I make the robot seem more real. That's the difference. Anthropomorphic and promote. Yeah, okay. So volts is what you're looking at with electricity. That's almost first every single time. In fact, voltage tells you most of what you need to know in troubleshooting. Why? You say, well, I need to know the amperage flow. Well, you can guesstimate amperage flow as far as, how can you say, not even a service value, but a service diagnostic of sorts by following voltage drop. Go all the way across the circuit, and if you're here and you've got your full volts across the battery or your source power, but someplace down the line you've got a problem, dim bulbs or something not operating, well, then you stay here. Then go to the next connection. What do you have? Well, if you still have the full voltage, because even if you got a problem with amperage drop, you're going to have 0 across your source. But you go to the next connection. What's that? Well, if it's almost the full voltage amount, or it's an amount here, then you can continue on down the line until all of a sudden you find out that, yeah, over here it's total potential difference, total voltage drop that it should be. But why? When something isn't working right on the circuit. You keep going out until you find the drop. Now, some guys like to hopscotch. I like to hook here and just keep going down the line until I find out where, yay, look, there it is. So, because if you go from here to here and you have 0, it means you have no current flow. Yeah. You're saying, wait a minute, you're talking about voltage. Exactly. If there's no voltage drop of any kind, then there's no current flow. There's no connection to the other side. So now you know you have a break in the system and you haven't even finished. Well, where's the break? Same idea as voltage drop. You got a bulb that's dim. You get down through from here to here. All right, you still have 12 volts. Or you don't have 12 volts. But whatever. You keep on going down the line, you find to where all of a sudden you got a few volts here, maybe. A few volts there, maybe. Then you go to the other side of the dim light bulb, and all of a sudden, boop! Hey, look at that. We got a perfect connection all the way back through source voltage. You know, somewhere between there. Because coming to the bulb, you should have full voltage, and if you don't, then you know you have a problem from there back. So that's, or you should have almost 0 volts going down. And if you start increasing in volts going down, then you know you have a problem. And you get to your implement, your appliance, bulb that's dim, and you hit on the end of it, and all of a sudden you've got 6 volts. It's going to be dim. That's all there is to it. So, but if you go all the way to here, and your voltage drop is, say, 1 volt or 2, or 1 volt usually, it's like a quarter to a half a volt per connection. So if there's 1 or 2 connections, you know you're going to have a little bit of a drop, but not enough to speak of. And most meters won't pick it up, the less expensive ones. So you come up to there and you have your almost 0 drop. So 1 or 2 volts might show up. Go to the other side of the light. Well, you're showing similar voltage, but not all 12. Keep hopping. Go down the line and find a connection. Hit the connection. All of a sudden, you have 12 volts. Yeah, somewhere between there and here, you're hop. Because some guys like to hopscotch down through, but I like to stay here and then keep going down and finding where the volt change is. And when the light gets bright, you know you have a full. And then you can hopscotch. You can say here is near 0. Okay, so you run out of space because your leads aren't long enough. Well, now you can go down to the next connection, and then you can do that. Just to me, it causes a little more trouble. But hopscotch, follow it. Someplace in there, you're going to find a voltage. All of a sudden, 12 volts is what you're supposed to have buzzing around the circuit, and you'll be going along. Excuse me. And on either side of the load, you should be getting your 12 volt drop. But there's a problem. You're not. Now you know the problem's still further down the line. Keep hopscotching until all of a sudden, oh, look at all the volts I wasted. I had 6 here, 6 there. Oh, found it. Then that's roughly how that's going to work. Voltage drop will tell you where your current flow problem is. Yeah, the bulb's dim. That's current. But the voltage drop gave you the resistance. You didn't drop your 6 volts at the or 12 volts at the appliance. You dropped 6. The other 6 was down here at a bad connection. And then sometimes you can take a temperature gun for you geniuses out there that like to play games and say, hey, you know, you don't even have to do that. Yeah, well, that's true. You take your temperature gun and go down through your little connections and you'll find a hot one. Amp flow. Now you have to have some type of inductive ammeter or a direct reader, and you better know if it's direct. You're going to take any part of the circuit out, for all that matter. You can do it from positive to the first connection, separate the two and put your ammeter in there, or on the ground side. Yeah, it's true. Amperage does not fall off. You have amperage flow from one to the other. Voltage is used up, but amperage is doing the work. Sounds funny, but it's true. The amperage is the electrons. The volts is the potential difference in electron flow. It's going to flow. Doesn't matter. What's a short circuit? That's a massive instantaneous voltage drop and full flow of amperage. And depending on your source, it's also an explosion or a fire or things melting and burning and you getting injured. Stupid. Be careful. So we got volts and amps pretty well covered there. What's resistance? Well, we just talked about resistance and our voltage drop. What is the resistance? Well, doesn't matter. You found your voltage drop area. You found the place. You clean your connections or change your wires or whatever's required. And the resistance is removed. Now you can measure resistance in your bulb. Well, you know what's funny? What's the resistance of the bulb? Volts equals amps times ohms. Resistance. Well, if you want to know the resistance and you don't know it, well, if you have amps, divide amps. Amps are up here, amps times resistance or ohms. Okay, well now divide it out. What do? Cancel them out. Bring them over here. Volts over amps. So you have voltage. You can test your amp flow, and that'll tell you your resistance. 12 volts, you got 2 amp flow. What do you got? 6 ohms resistance. That's simple. Crazy as it sounds, write it out on paper. Volts equals amps times ohms. Or volts equals amps times the resistance in ohms. And then when you want to know ohms, well, divide by A here. Scratch, scratch. Divide by A there. Volts divided by amps. You want to know amps and you know resistance? It'd give you a rough idea if you know the resistance and how many volts you have being used in the circuit. And do it the other way around. AR, divide by R, over here, V over R. Volts divided by, and just keep messing with your formula. So you get volts, amps, and ohms that you can get just by knowing 2 of the factors. It'll give you an idea. So you're sitting there in the circuit wondering, well, just pull it out. Well, sometimes your lights are up there in the head, you know, and you got to tear everything apart. Well, if you got the time and you can do it, sure. A direct reading is better, but if you don't know it all, you can put your amp clamp on amp reader, or your direct, if you already know it's not pulling that many amps, because you're going to blow a fuse in a direct. The other one, you just peg the meter and, ooh, wrong range. That is in your inductive. And now you'll have an idea, but it's just simplistic. Well, what's the watt of the light bulb? Well, watts is usually input power, is what they're considering. So, if you know you have 2 amps coming in on 12 volts, volts times amps is roughly watts, especially in a resistance circuit, such as lights, incandescent lights. So what do you have? 24 watts. You got 2 amps, 12 volts. You say, well, when you turn the alternator on, it goes up higher. It do. So you can take a little more amperage and a little more voltage. So measure them. But you're going to come up similar. And they usually end up, 24 will end up probably in somewhere between 25 and 30, depending on how hyper your alternator is. But still, there is, by the amp flow, even with the key off, by the amp flow and what's in the bulb, you have your resistance. These values can change, but when they divide out, you're going to come to the same resistance or similar anyway. So if out in the field, for lights in particular, it doesn't matter that much. You say you're doing a CAN network circuit. Checking your ohms. Guess what you discover? They'll operate pretty well between 58 and 62 ohms with 120 ohm resistors on each end. They're not exactly accurate, are they? And the system will still function. So you have to understand those things. Same thing with the resistance and voltage amp changes. It'll change a little bit, but still, it's close enough. It'll work. Watts. You want to know the power of the light bulb. Well, watts equals volts times amps. So, like I said before, you've got 24 amps. Your resistance, similar, or 24 watts, I'm sorry. So, you know your volts, you know your amps, now you know your resistance, now you know your watts, and what have you done? Formula, you barely even turned the power on. So that's after you fix it. Before you fix the circuit, you go to check your amp flow, and there's almost nothing. That'll tell you there's a voltage drop too. You got a dim bulb, you got so many amps, so you know you have to have more amps than that. And your voltage is still good at the source. Now you're going downhill to find the rest of it through the circuit. Watts, it's very simple. And you say, well, in inductive motors and inductive loads and electronic stuff, it changes a little bit. But for the most part, that's what you're going to have. Volts times amps equals watts. Your watts input to the motor. So if you look at a motor and it says it draws 10 amps on a 120 volt circuit, you got about 1200 watts you have to have. Another thing you also know is, startup. What's the startup? Guesstimation always is double. DC or AC, doesn't make any difference. Your startup, everything from standing still to charging the whole winding, the entire windings, and then getting the motor and rotor turning, just double the start, initial surge. You'd say, well, that's not always accurate. No, it's not. But it is pretty good. And if you use that formula, it'd be all right. We did that one time, and a guy told me, young punk, he got all twisted. No, that's not exactly right. And I said, no, it's not exactly right, but it'll get him going. Well, the other guy, fortunately for me, the customer was one who was a little bit more intelligent. He'd had some schooling too, and a little bit of experience. And he said, will this generator start this pump? And I said, well, maybe. What do you mean? And I gave him the same thing. Volts times amps gives you your watts running under full load. He said, yeah, but I said, your startup's usually double that. So he says, oh, I got to have so many thousand, I forgot what it was. It was pretty high. It's about 15,000 or something. I said, however, you might get away with it. And he said, how's that? I said, this is a centrifugal pump. And if it starts up mostly dry, I said, you should be able to fire it up. Once it's running, you had plenty of generator to run it. The only thing is starting. And I said, if you can get that thing drained out and start it up each time, you might even find out later on that it can start it up, especially if you have a siphon. And he started thinking and looking, and he says, so in other words, it might work. I said, it's sketchy, but it might. He bought the pump, fired it up, and he says it works fine. But he says it is a little hard on startup. So he says, I'm good. because once it starts, I don't want to shut it off. So he says, happy as a clam. The kid was having a fit upstairs because not everything is that clear or perfect. Yeah, actually it is. It's that clear, it's that simple, it's not necessarily perfect. When the customer understood that, we got along fine. But that little punk, oh my, he was mad. He had to make a phone call too, to be sure. Facts are facts. Customer took a chance, it worked. Now out here, I have another unit that my generator says no problem, should fire it right up. Doesn't have quite enough startup. What do? Well, it's a motor. It's on a belt sander, big cylinder head belt sander. Well, it's not huge, but it's good size. What's it take? 48-inch belt, 15 inches, 16 inches wide, so it's good size. So what do? I hit the start and give it a shove. Takes right off. Once it's going, it works just as well as it ever has. It just needs that startup power. All right, let's get from that. We're going into the hydraulic section like I was talking about before. Now set 0.7854 times diameter squared. That can give you an idea. Measure your circumference, divide by 3.1416. It'll give you an idea of your diameter. Going backwards, okay? Pi, 3.1416 times the diameter gives you circumference. So go backwards. Anyway, once you have that, you got an idea of your diameter, 0.7854 times the diameter squared, which is an interesting formula that technicians and engineers seem to like to use rather than your other pi r squared. But pi r, you're talking a perfect circle, you can measure the radius, you can, and so that's why we use 0.7854 out in the field. It's easier to find diameter than radius. Because you get the radius from the diameter, why not just take it, right? Why have one more step of calculations? 0.7854 times the diameter squared will give you the area. And now get the depth. If that's a 1-inch depth, then there you go. You've got your cubic inches inside that pump. And then it'll give you an idea, a rough idea, the cubic inches in the pump, how many per circulation that you're going to run through that thing per revolution. There's another formula in there for 0.7854 times diameter squared to give you, then times the depth to give you an idea of the cubic inches available, gear, and there's a formula that Parker Hannafin has in there that'll tell you roughly what the gallons per minute flow of that pump is, and it works well with vane pumps and gear pumps. We used to do it in college constantly. We don't do it anymore. Why? Because pumps have a tag on them with a rating. But that's just a formula you can play around with if you feel the need to in certain areas too, because you can get the area cross-section of a hose to find out what its nominal size is, or roughly the nominal size, to give you the gallons per minute flow that can go safely through that hose, because Parker Hannafin, Gates, and other companies, Weatherhead, they have charts to give you flow through a hose, suggested maximum flows through the hose. So that's something you can do if you're putting thumbs or other rotators and such out on the end of an arm to give you the amount of flow that you want, or the amount of flow you don't want. Which, how can you say it? Load sensing systems, your pure load sensing systems, you can put smaller hose to reduce the flow, because if there's enough back pressure in the system, the pump just backs right off, and then it only flows out what you request to turn that head. And you can cut down on your flow, which cuts down on heat. Gotta. So, what's the next thing? Your formulas for pressures. Flows are in gallons per minute or liters per minute. We can play with that one all day long. Gallons per minute. What's that? 32, 64, 128. What was it? 128 ounces per gallon. A gallon per minute. You can cut that down into gallons per second if it's really fast. But usually gallons per minute is what you want to know. The displacement of a pump is done in cubic inches, or cc's, per minute, or per revolution, I should say. And there's your gallons per minute that you can calculate from that. What's the RPM of the pump? What your cubic inch displacement is. So many cubic inches, get your formula. You'll have to go on the web for that one. It'll tell you how many gallons per minute a pump is capable of at a given RPM. And they all have a maximum because they start to cavitate after a certain point. Draw in oil faster than it can be supplied through the inlet port to it. So gallons per minute, liters per minute, just simple. Just don't complicate it. I know 0.846 or 0.864 quarts per liter. Whoop-de-flip-and-do. Round it off to 0.9. How close are you? You're at 0.9. Give it up. So if you got 20 liters per minute flow, fine. That's 80 gallons a minute. Don't overcomplicate it. If you want to, go ahead. But what are you going to come up with? 75 to 80? Whoopie-flip-and-do. The only time that might be a concern is when you're way down there. You start getting below 15, 20 gallons a minute, it might be a problem. Usually, no. Why? Because there's enough losses and frictions in the system and inaccuracies that it's going to be pretty dang close. So, I'm going to stay with gallons per minute, your flow rate. If you go to Parker, you're going to find a horsepower. There's a horsepower calculation that we used to use in college that I don't remember what it is. But it would tell you that so many gallons a minute at 1,000 psi. And what we used to use as a general rocket brain formula was, if you had 20 gallons a minute at 1,000 psi, you needed 20 horsepower. And that was an electric motor conversion. So what did you need? You need 40 internal combustion horsepower. Diesel, gas, propane, whatever, you need 40 internal combustion horsepower to run 20 gallons a minute at 1,000 psi. You say, no, wait a minute. Nope, because now take it to 2,000. Yeah, now you definitely need the 40 plus horsepower to run it. You don't know how much, but that gives you an idea that 40 internal combustion is to handle the surges and such that come with it. Electric motor doesn't care, it draws more amps. Just that simple. So you got a 20 horsepower motor running 20 gallons a minute at 1,000 psi. We'll go to 2,000 psi. Yeah. Now you need 40 horsepower on an electric motor. In gas? Yeah. You want someplace between 1.5 and 2 times to run it and still be able to capably run the thing up to a good amount of pressure to handle. So those are some ideas to keep in mind there that are very simple. You say, oh yeah, but no, your excavators, you can have a 150 horsepower engine with a 100 gallon a minute pump. And you say, what? And some of them have a lot higher. But they count on the control system. As the pressure goes up, the flow gets kicked back. So the engine starts to snort, and it kicks back the pump at a controlled rate. How does it do that? The older pumps use engine RPM. The newer pumps have an algorithm in the pump itself, gets to a certain pressure, it knows the engine's working, it knows the engine came down to a particular level, then it kicks in this program to maintain that minimum engine RPM. You say, yeah, that's correct. An engine might be wound to the pin, 2,500 RPM. It lugs down to 23 or 2,200, whatever is given its maximum. And then the pump will start to de-stroke whatever an RPM before that. And when it gets down to that minimum level so that it doesn't burn too much fuel or work too hard, then it'll keep the pump moving back and forth in this range to keep it from hitting that. And then if it can, you can hit usually what they call an eco level, fuel saver. Then they'll take the pump and de-stroke it even faster and keep the engine up at another RPM higher. So there you're working with your gallons per minute by your RPM and the load and everything else. So the engine can calculate the load, send it to the pump controller, and do all kinds of calculations from that point too. But usually they just pick RPM. So you're talking pressure flow differentials to maintain that horsepower usage. Just like I told you before, 20 gallon a minute, 1,000 psi, 2,000 psi. That 20 horsepower just turned to 40 just that quick. Well, same here. You got a pump capable of 100 horsepower. You got 150 on it. Not enough. How does it run it? Well, pressure goes up, flow goes down. It's designed to do that either. Most of them are designed to do it both electronically as well as hydraulically or mechanically. They'll have a pressure compensator in there to drop it off when it reaches a set point in it to back it off. But then again, electronically they'll have it so that they can play within the range before it starts mechanically compensating for the pressure to maintain horsepower of the engine and stop fuel burning, etc., or stall. I see. Excuse me. It had one with a 75 horsepower engine and I think a 40 gallon a minute pump was what it was rated at. Dual port pump, but rated 40 some gallons a minute. And it was a PC78 Komatsu. Fire the thing up. Sits there running fine. Swing fine. Blade will go up and down fine. You hit that closed center load sensing system lever on the pilot control. Just bang. Yeah, no, it was a 54 horsepower engine on like a 38 or 40 gallon a minute pump. 54, 60, but it was pretty close. So you just pull that lever, boom. Didn't even have time to compensate. Why? The pump never changed. The pump didn't pick up a load. Well, one of the control pistons, there were two that were supposed to control the pump, fell out and turned sideways, and the pump was set like 3/4 stroke. So you'd fire it up, and running full throttle, you could move it a little, and that engine would just about die. But if you were anywhere below half throttle, that it was funny. I'm laughing. What are you laughing about? Figure it out. Yeah, pump's junk. We got to tear it apart. So Komatsu said no, and that's why you check your horsepower. You get an idea of your horsepower relationship, what you have for pump flow, pump's pressure capability, and the engine that you have connected to it if you don't know anything about the machine itself. You find out how many liters are in the engine, or cubic inches, whichever way you want to go. And that'll give you an idea of, just say, a 15-liter engine on a bigger machine, like, but that's a monstrosity. Let's go with the 12-liter. Yeah, 12, I think. Trying to guess, but there was one Komatsu engine that was right around 11 or 12 liters. So you know it's around over 600 cubic inches. You know the thing's capable of about 250, 300, maybe 350 horsepower. So now you got an idea. That pump's got some dang flow in it. Yeah, you got two pumps that are capable of over 100 gallons a minute each. 200 gallons a minute. You're sitting there. How in the world? De-stroke the pumps. That 300, 350 horsepower engine will handle it. But now that you know the capabilities of the pump, the pressure it has to run at, horsepower of the engine that it's supposed to be roughly, now you can get an idea of what to do with your control systems. If you can figure out either the load sensing, how much load, how fast it comes in, and the maximum that you can demand on your load sensing side. Then on the other side, your pressure compensation side, your horsepower preserving side, I should say, control, then you know how much to back that off or turn it up depending on how the engine's running. If somebody's complaining it doesn't have any power and you listen to it, the engine barely changes RPM under full load and the relief valve blowing off, or if you have multiple functions going and a lot of flow, that the pressure's lower but there's a lot of flow, that's usually where you get most of your hard work. Tracking is another one. Counter rotating, driving straight ahead, backing up, and all those will give you an idea. If your engine, if it's doing it but it's not impressive and your engine's not even working, now you know you can take your horsepower compensator and crank it up a little. What's that mean? It means more flow at the working pressure you're at, and the engine's going to work harder. Well, you can only go to a certain point, because I've proved that to people before, where you can only go to a certain point where that engine's working hard but the RPM comes down and you lose flow faster than you gain by lugging the engine, thinking you're turning the pump on farther, but the RPM came down. Well, so did your flow rate. So there's a little play in there that you need to stay with. That's why they have the load sensing and pressure compensating or horsepower compensating, the electronics, keep that balance so the flow is up near where the pumps can go to maximum without a problem if they ever need to, because the engine's there. The engine's not lugging down too far. And an engine internal combustion needs to lug so far anyway, because that's how it produces power, is pressure in the cylinder. And if it's already at a particular workload, then that means it's already primed so that when the next one hits, the governor opens up, it's there. The turbo's at speed, the engine's at speed, the fuel system's at speed, or delivery rate, whatever you want to call it, and you get better response. Okay, so that's the simplicity on that one. We can go into the others as much as we want, but those are the main things on the formula that Parker Hannafin's going to have. Now, another one that's important to you, you walk out and you see that the system is in bar, B-A-R. You look for system pressure, it says bar. 10 bar. Well, okay. What's 10 bar? 1450 psi. Good. A bar they consider in Europe, and this is, I think they did it for simplicity, but it was an average. Sea level average in Europe, absolute pressure gauge reading is 14.5. So that's what they used for standard over there for bar is an atmosphere. So there's, just like our country, there's bar absolute and bar gauge. But they very rarely say anything about either one unless bar is labeled absolute. They just consider it bar. So like I said, if you have 10 bar, in our translation is 1450 psi. Why do they do that crap? I don't know. But over here, we do something similar. 0 is 14.7 psi. And absolute begins the reading at 14.7 psi. So there's PSIG gauge starting at 0, general sea level of atmospheric pressure. Just zero it out because you're reading from there on up in your machines that are sitting here. You don't need absolute. In fact, absolute screws things up until you're talking turbo and intake flow and such. Absolute begins at 14.7 psi, which, strangely enough, translates over into, what was that one? Kilopascals of 100 in Europe. When they change scales, they go to kilopascals, 100. We'll get there. So you've got 14.5, 14.7, and 100, your basic three numbers. Yeah. What's an actual Pascal? Don't know, don't care. No, I'm going to try and simplify this one for you. Bar is an easy one. Most of the European community uses bar. Deutsch used it. Once we learned it's 14.5 psi per bar, oh man, our translations and working with Deutsch was easy. Liters per minute. All right, got 20 liters per minute. 5 gallons a minute. Boom. You know, it started getting very, very easy. Now, sometimes, you know, you're getting too many decimals and other things in there. I pulled out the calculator or the paper and pen just because I didn't want to think that hard. I was already trying to troubleshoot. If I'm trying to troubleshoot here, put your stuff on paper and use the calculator. Because if you mess that up, then all of a sudden your conclusions are wrong. So with Deutsch, it was very, very easy. They still use volts, amps, ohms, watts, just like we do over there. So that part, that's irrelevant. But your pressures, that's where it really gets sketchy. What, you say there's other flow rates? There is. cc's, milliliters, are fluid measurements. And you can do those per minute if you want to, but liters per minute, they're pretty much. And milliliters, you know what that is? That's 1,000th of a liter. So I can't tell you what that is in ounces. Don't care. You're looking to match a spec. cc, cubic centimeters, is identical to milliliters. There is no difference. Don't tell me there is. There isn't. One's a fluid measurement and the other's a volume measurement. That if you poured the fluid into that volume would give you the same measurement in milliliters as it does in cc. So give it up. Yeah, they jackassed the system. So go back to your liters. We've got that part. Now pressures. Why do I give you the milliliters and cc's? There was a video on Instagram, I think it was. Beautiful. Deutz used to use a tube on their injection pumps to help with their timing. You put it on number 1 cylinder, which on Deutz is the back one, and you turn it up, you bring fuel into the tube, and then you'd either turn it around 2 times or 1.75 times, and then turn the thing up until you got fuel in the tube, bring it to a mark, go all the way around, mark it, and then when it starts to move that fuel from this graduation to the next graduation, then look at your timing on the engine. And that would be your start of injection time. Well, for your common rail systems, they've taken that tube, and because it's sold little in the automotive world, in the smaller diesel engine world, they put it right on top of the return of the injectors. And that tells you how fast that fuel is coming out the return of the injector, and gives you an idea, like they showed on the video. It was beautiful. 2 of the injectors, one of them filled the tube right up in a few seconds. The other one took a little over 5 seconds to fill it up, and the one in front hardly had anything coming out, and the one behind it had, you could see just a little blip now and then. In other words, these 2 were working close to what they should. These 2 were way out of line. Burning too much fuel through them. Why is that significant? Because your fuel pressure pump, it has to push too much fuel to maintain the pressure for the injectors to work. And it's working too hard. Meaning that if it's already working at this high a level, it's supposed to put out this much fuel. Now it has to put out this much fuel to keep up. You lose that gap in there between full power output, because instead of full power output being here, now it's up here, and the pump all of a sudden reaches the end of its limits. Why? Pressure flow. That's right, your pressure flow. How can you say it? Relationship. Same thing. They have to have a smaller pump to develop 30 to 40,000 psi of full rail pressure and still be able to deliver the cc's or milliliters per second or per injection, which is another ironic one, because you measure milliliters over here in a beaker, and then they'll tell you how many cc's per injection stroke goes into the engine under full load. Yeah, they didn't help us at all. So that gives you an idea why we're looking at it. Now, why are we looking at 30 and 40,000 psi? What are they looking at over there? Bar. So divide by 14.5. You've got your final bar reading on 30,000. I'm not going to calculate it for you. You got paper and pen. You got a calculator. So what's the next one? Well, you look at another one, and there's this big M and a small PA down here. What the heck is that? Megapascals. Remember before I talked about kilopascals being 100 at sea level, and our sea level 14.5 psi, and 1 bar in Europe of 14.5 psi. Those 3 readings are equivalent. Well, here we are from the kilopascals of 100. Now we're here. Well, ours here in this region in the river valley, ours is 98 to 99, depending on the day and what hill you're on, literally. So we're just a little like 900 to, I think the highest point around here is 1800. You go into Pennsylvania, it's a little over, it's 2200. So there's no real high points where we are. But still, it'll vary, 96 to 99. You need to know that to give you an idea what you're reading on absolutes for your turbocharger and your manifold pressures. You turn the key on and you've got it set right there, and it says, wait a minute, 98? What the? Yeah, absolute. You fire it up and the number goes up, then you know for sure it's absolute. Makes a difference. You need to know that. So now we've got bar and PSI. What's next? Well, quite often you're running into the megapascals. What's the conversion? I've got a megapascal. What is that? A megapascal is 1 megapascal is 145 psi. Ah, some of you caught that, didn't you? A bar is 14.5. A megapascal is 145. Now you're catching up. Yep, a megapascal is just 10 times the number for a bar. What a bunch of morons. So I don't know what to tell you. So you can do the conversion if you want. I don't care to. Now there's another one that's you'll see kg/cm squared. That's kilograms, like weight, per centimeter squared. What was it? 2.2 pounds per kilogram. Yeah, no, just skip that. That means nothing at this point. Kilogram, its weight, times a centimeter squared. 1 psi. This is bad. I mean, somebody should have been shot in the nuggets for this and castrated beyond afterwards. 1 kilogram per centimeter squared, kgs as the people like to call them, /cm squared, is 14.225 psi. We having any fun yet? The absurdity of it. And of course, kilopascal, we already have a number for that. 1,000th of a pascal. Just don't even go there. You can. It's amazing to me. So you have 1,450 psi. Start playing around. You have very few pascals, don't you? Or very few megapascals. So you're into 10. But you have to remember 10 megapascals is 1,450 psi. You can't just look and say, I don't care, I don't want to figure it out. No, you have to know. That's a huge discrepancy. Huge. Don't go playing around. You're into the inject into my finger oil range if there's a leak. Okay? It's dangerous. You say, well, it's not much for work or anything else. But if you're stupid, it can get you injured. Lose a finger or hand. So don't go screwing around with this stuff. Kilogram per centimeter square. Well, you already know that's going to be a little bit different number, aren't you? 10 of those. It's going to be, yeah, but this is a little higher. So it's going to be probably 11 or 10.5 or something. So you've got that already that, okay, we're in this ballpark no matter which measurement we use. So that's how things get screwed up with this. The numbers are funky and some guys get all twisted about them. I know one guy, I looked at him and said, okay, we got such and such. See, that's not the exact number. I said, no, but it's close enough. He said, oh, it's at 14.225 and it's not. Look, you want to use kg, knock yourself out, okay? I got a megapascal number and you want it in kgs. So it goes to 14.60 instead of 14.50. Yeah, it's a different number. It's 10 psi. Please. Okay. Yeah, and I'm going to change jack. That's my point. So now we've gone from psi and bar, megapascals, kilogram per centimeter square. So we're all in the ballpark of a lot of this stuff. Now the other one that gets really confusing, and you're better off converting it, when they start looking at you and saying cubic centimeters of mercury, or inches of mercury, inches of water, cubic centimeters of water. That's different measurements altogether. What is it? That's manometer column. Just like taking a tube with graduations. Millimeters. And mercury is totally different than water. And there's conversions, and my basic thing is read it. One of two things: either pull out your calculator, go to a chart and convert it and follow it on the gauge, or get yourself a manometer, proper one, and read it direct. Myself, you get one of the electronic gauges, pay the dang money. They're anywhere between, I think, $200 and $500, $600, $800. If you get a fluke, way up there, like over $1,000. You get a Tifco, they're lower, but they're still pricey, $5, $6, $7, $800. And I can't remember the one I bought. It was off of Amazon. It turns out it's accurate. It's pretty accurate. So, and every time you fire it up, it's supposed to zero. Well, mine's a cheap one. It doesn't. You zero it, you're all set. A little while later, it says 0.1. I don't care. Even saying 1 when I'm looking for 500 psi and it's 501, please. So get yourself a good gauge and get another gauge that you can compare it to. Have something else that you can pressurize and check 2 gauges to be sure. I want a hard gauge only. Well, go ahead. I don't care. But let me tell you, the frequencies of failures with the electronic gauge is either dropping or forgetting to replace the batteries. Frequencies with hard gauge, it's done. I had one I used continuously, worked perfectly. Took it up to another place to measure a lower number than 2, 3, or 1,500, 2,000, 3,000. Wouldn't do it anymore. 3,000 pound gauge, and I was just looking to go up into about 800 to 1,000. Nope, not a one. Wouldn't even read 250 that I knew I had. So I got another gauge. We checked that gauge, didn't work. We remembered I had the other gauge, put it on, got my number. And we knew part of a system was working properly. And that's what the customer was looking for. He wanted a information diagnosis as far as where to start going from there. Excuse me. We're at the point where we got to tear it apart, at least partially, to even continue testing. Forget it, then I'll just tear it apart. Okay, we did. I got paid. I don't mind. He says, do you do work like that? And I said, well, if you have the crane and the proper equipment here. I said, I don't have anything that's transportable like that anymore. I used to. It got stolen by a Christian. Wesleyan Christian. No. So that's where we're at with that. Anyway, pressure is important. When you're down into the lower PSIs and you start measuring in water column and mercury, those are 2 different things. And you say, well, what in the world? No, your blood pressure cuff? Millimeters of mercury. Hg. That's what that is. You say, but that's on a gauge. Go in the old-fashioned doctor's office. Mercury in a tube. It needs, all it is a vented tube. It needs, why they do that? It needs no recalibration. Ever. They'll check it anyway, but they never need recalculating. If you lose a little mercury, something leaks out, well, now you got a little bit of a problem, but still, you're just moving mercury from one location up into the tube, another. Millimeters of mercury. Well, if it wears the inside of the tube, now you got more mercury, it'll give you a little off reading, but in general, it needs no recalibration. So that's why they like to use water column and mercury levels of inches of mercury, inches of water. Inches of water is a lower pressure, very low pressure reading compared to mercury. And then you can go into, sometimes they use manometers like that in reverse, where the tube will go up, circulate over on the other side, and it'll draw so many inches of vacuum. I know, usually you just use a gauge that reads in inches of vacuum. So, but some will say inches of water. Well, now you need to know that vacuum as well. We have that with a radon vacuum deal down in our basement. So anyway, that gives you an idea of your pressures. Vacuum, I just talked to you about that to some extent. but vacuum also includes kilopascals and columns and inches, and it gets into some funny stuff, but usually almost all of them end up defaulting to inches. But why do we use water column? Well, the same thing again. You have a pressure gauge that you're trying to measure very minute pressure differences sometimes, or just plain minute pressure to begin with on airflow or exhaust flow. That's one of the ways they find plug catalytic converters. I missed one time because I didn't know it was there. It was in a truck that was never supposed to have a catalytic converter. He said, yeah, it's tucked up in the hole. He says, you probably wouldn't have even seen it. Plugged mufflers, plugged exhaust systems on some of the turbo diesels and such. That's what they're going on about. So you can poke a hole in the side of one and put a little fitting in there, and you can check your back pressure on a minimal. And on some of the turbo diesels, oh yeah, they'll build some pressures for you, trust me. You want a pressure gauge on there. But you still need a spec. So a lot of this means nothing if you don't have a specification, you don't know what you're troubleshooting, or you don't have any idea what you're working with in the system. So pop your doors open, go check the general performance of the machine. And now we're talking both electrical for engine operation, electrical for pump function. So some of these things you're going to go through all this troubleshooting, and you know what you're going to find out? Like I did one time. I walked up and I looked at the operation of the machine. Something seemed funky. I walked up to the top and tightened the alternator belt and changed the entire operation of the machine completely. So that's why I go into volts, amps, and hydraulic pressures and such so often. Maybe later on we'll talk some compression sometime. I'm coming up on an hour now. Wasted that much time out of my day, which I planned on doing at a certain point anyway. You folks be good. Peace out.